Okay, all right, so we're being live streamed. So in the meantime, let me make Celia Epps. Okay, we have to add one other person and then we'll be good to go. Okay. Oh, hopefully, is anybody else hearing that background echo or is it just me? Okay, cool. It's just me hearing something in my head. Okay, sorry, let me exit off of this. All right, okay, let's get started. I'm gonna share my screen. Share screen, okay. All right. Oops, sorry, Zoom is in the way. Okay, all right, so I think we have everything set up. Sorry for the delay. So I wanted to welcome everyone again to our 2023 Black Space Week Undergraduate Research Showcase. Myself and Rob Washington will be moderating for today. And so I am the Vice President for Black and Astro. And Rob, do you want to introduce yourself? Sorry. And I guess Rob is trying to get some audio set up. So Rob is our public relations chair for Black and Astro, and we hope you all have been enjoying the week. So just some housekeeping. We're going to have presenters, and then we're joined by Vietman Barber for our captioners in ASL. So I'm really thankful to them for helping us to make this event accessible. So we're going to start with introducing our judges. What will happen is that each presenter will present for about 5 to 7 minutes, and then we'll have questions from our lovely judges. And then the audience is also welcome to ask questions as well. All right, so to get us started, our first judge is Kirsten Boley. So Kirsten is a rising fifth-year astronomy PhD candidate and NSF graduate research fellow at The Ohio State University. She studies the impact of elemental abundances on planet formation and evolution with Jesse Christensen, Wendy Pinero, and G. Wong. In her free time, she enjoys painting, dancing, and being a plant mom. And fun fact, she won our art competition last year. So our next judge that we have is Kiera Wilk. Kiera, her, is a third-year planetary science PhD student at Brown University. She uses a combination of laboratory and remote sensing observations to study water on the lunar surface, in addition to detailed geological mapping of the surface features of Europa. Kiera is an affiliate graduate student on both the Lunar Trailblazer and Europa Clipper missions. And our last judge is Gianni. So Gianni is a rising third-year physics PhD candidate at Florida Atlantic University. She is currently working with Dr. Vicky Serradini, who her research entails understanding the seeding mechanisms of supermassive black holes by studying their AGN occupation fraction and dwarf galaxies. She likes to write poems and go to the gym during her free time. So these are going to be our lovely judges for this event. So we're gonna get started with our first presenter. So first up we have Kiana. So Kiana is broadly interested in cosmology and galactic/extragalactic astrophysics. In particular, Kiana has experience in 2 subfields. In the first, she works in large-scale structure cosmology research, where she focuses on constraining 3/2-point correlation functions, accounting for second-order deflection effects in DES-Y3 data. On a slightly smaller scale, she works in galaxy formation and dark matter research, where she focuses on constraining the Milky Way subhalo population to improve future dwarf galaxy observations and shed light on the nature of dark matter. She is primarily a computational astrophysicist, utilizing simulations, programming language, and computation analysis of cosmic survey data to build and refine theoretical models. And she is currently a student at the University of Chicago. So I will let Kiera start. I will stop sharing screen. And Kiera, you're welcome to share your screen and present to us. So let us know if you have any issues with that.
Hi, everyone. Can you hear me? Okay, cool.
Sounds good. Yep.
Okay. Can you see my screen? Sorry, okay. Hi everyone, my name is Kiana. Today I'll be telling you about my project investigating LMC subhalo population evolution in the context of the Milky Way, a project that I started last summer at Stanford with my mentor, Risa Wexler. So the way that I love to introduce this project is that it's a project to understand dark matter. So dark matter, as we know, can't emit or absorb natural light. So the only way that we can observe it is by relying on how it interacts gravitationally with the matter that we can see. And as it turns out, there's a direct relationship between where dark matter condenses into these things we call dark matter halos, and where galaxies form. And we call this relationship the galaxy-halo connection. And we can actually use this relationship to study dark matter. So the Milky Way's dark matter halo contains the Milky Way galaxy, of course, but it also contains smaller galaxies, which are also contained within the Milky Way halo that we call dwarf galaxies or satellite galaxies. And they actually have their own slightly smaller halos. So we call these smaller halos subhalos because they're smaller halos inside of the larger Milky Way halo. And by getting precise measurements of how many satellite galaxies are in the Milky Way halo, we can, by proxy, get an estimate of how many subhalos are in the Milky Way halo, which means we can get an estimate of how much dark matter is in the Milky Way, where it is, and how it's distributed. So previous studies, looking here at my abstract, previous studies of dwarf galaxies have determined that in order to accurately constrain this quantity, this Milky Way subhalo population, we need to take into account two significant effects that are present in our actual Milky Way galaxy. So the first one is the Large Magellanic Cloud, which is the Milky Way galaxy's largest satellite galaxy. It's estimated that it fell into the Milky Way halo about 2 gigayears ago. And with it, it brought in a ton of subhalos of its own. So if we want to get an accurate reading on the Milky Way subhalo population, we need to take into account, well, how many subhalos did the LMC bring in? Where did they go? And how did it change the overall distribution and population of the Milky Way subhalo population? And on the flip side, we also have this huge disk at the center of the Milky Way galaxy that we call the galactic disk, where much of the mass in the galaxy is concentrated. So because of tidal forces, we know that any subhalos in the Milky Way that are close enough to this galactic disk will get depleted. So we'll cut down on the overall subhalo population in the Milky Way. So these are two competing effects that are present in our actual Milky Way galaxy. And so if we want to accurately constrain the subhalo population in the Milky Way halo, we need to take both of their effects into account. So the way that we actually build this model is by utilizing what we call zoom-in simulations. So these simulations are crucial to the kind of work that we do because it grants us access to get up close and personal with the Milky Way in a way that we can't always physically with telescopes. And we can do so more efficiently without having to rely upon waiting for years to get survey data or waiting to get improvements in our resolution for our telescopes. So if I can direct your attention to this image here with the 4 panels on the left side, these are 4 panels of a simulation of a halo. And on the top left, we see a dark matter halo simulation. So that's a type of simulation where it just takes into account all of the dark matter in a particular halo. And on the right side, in the top right panel, we have the same halo, but we have an embedded disk potential. So what that means is we wrote some functions and put it in the simulation, and it's supposed to simulate the galactic disk that's actually at the center of the Milky Way. And so comparing these two, you can't really see much of a difference between the halo with the disk and without it. But in the bottom panels, if you zoom into the center of the halo, so this zooming in is an effect of a particular simulation that we use called zoom-in simulations. If you zoom in, you can see that, oh, when you actually add a disk, there is less substructure around that center. So the substructure meaning less subhalos. So these are the 2 different types of simulations that we use in this project. And so going down to the methods and materials, I don't know if you can see my cursor here, but I'm circling it. We used 3 different simulations. The first was just modeling the Milky Way halo with the LMC. The second was the isolated LMC, so the Large Magellanic Cloud, before it fell into the Milky Way halo about 2 gigayears ago. And then the third simulation was the Milky Way halo and the LMC with an added disk in the center, which is supposed to model most accurately how our universe looks or how our galaxy looks. And so the way that we actually build this model is that we perform two different types of statistical analyses on them. So these bottom two plots here are these statistical analyses. On the bottom left, we have a plot that measures as a function of mass how many subhalos we actually find in the Milky Way halo in the simulation, how many subhalos we find as a function of mass. And this function is called the subhalo mass function. And on the right, we're measuring how many subhalos we find within a given radial distance from the center of the halo, and that's called a radial distribution function. So zoom-in simulations and these two statistical functions are the tools that we use to actually try to get a number, constrain the Milky Way subhalo population. And so my role in this project was to create pipelines, so to actual program scripts that would go in and measure these two functions in each of those three simulations, and then compare them and see the results that we get. And so the plots here under the results, I said results, but these are actually just like working plots. They're very preliminary. I'm still working on this project. So these plots that we get are the actual deliverables that we should expect. But in the top two plots here, these were very early on, the plots that I got after I had first written the pipelines and then run them. So in the top left, we have a plot of the Milky Way halo with the LMC and no disk. And in the top right, we have the Milky Way halo with an LMC and we have the disk added. And if you haven't already noticed, there's something very wrong with these plots because they're the exact same. So this is telling us that the Milky Way subhalo population did not change after we added a disk. And we know physically that's completely wrong. So that told me that I had to go back in my pipelines because I had some bugs that I had to fix. And so I spent the majority of last summer really trying to refine these pipelines and get the statistical functions working with these simulations. And so if I can direct your attention to the bottom right plot, this looks more like what we should expect. This is showing the two same plots above, but in the same plot, and I'm comparing them. So the blue line is the Milky Way halo with an LMC with no disk. And the black line is the same halo, but we added a disk in. And you see, we do indeed see some depletion. So in the y-axis, there's less subhalos in the black line. However, over the course of the summer, there was some complications with actually on the back end programming the simulation with the added disk. So my mentors, he was in charge of creating that simulation for me, and he pushed it to me so that I could run my pipelines on them. And over the course of the summer, he had to keep pushing me more updates to the simulation because he was coming across a lot of complications with coding them. And so eventually we decided, I think adding in the disk element of this project is a little more complex than we had anticipated. And so we pushed this component of the project to the side. And now we're just focusing on really trying to constrain the LMC component of the project. So what impact does the LMC have on the subhalo population? And so on the bottom left plot, this looks something more like what we should expect from these pipelines. So it's showing, the blue line is showing the LMC halo or the Milky Way halo with an LMC. And the black line is showing just the isolated LMC. So before it fell into the Milky Way halo 2 gigayears ago. And we should expect that because the LMC is a smaller galaxy, it has fewer subhalos, that it should be lower on this y-axis. So the plots aren't finalized yet. We're still very much working on them. So the plan moving forward is to, one, finalize all of my pipelines so that when I run these statistical functions, we can rely on the results that we have. Number two, I actually have to create a new pipeline that goes in and explicitly tracks every single subhalo that the LMC brought into the Milky Way, starting from when it fell in all the way up to present day, so that we get a snapshot by snapshot image of how the Milky Way subhalo population changed over time as the LMC actively fell in. And once we sort of get these things finalized towards the end of the summer, we'll be working on a paper to wrap this up. And a natural offshoot of this project is then to consider the second order higher effect of, okay, we've constrained the impact that the LMC has on the Milky Way subhalo population. So now let's add in the disk back in and see how that changes with the LMC accounted for. And that's my project. I'm happy to take any questions if you have them.
Thank you, Kiana. So, judges, if you have questions for Kiana, please just unmute yourself and direct them towards her.
Hi, Kiana. Great. Love your poster. Your project sounds super interesting. I had a question about kind of, and I know that you talked about it earlier, but what the main question will be once you're able to actually put in the additionally add the what's going on with the disk and the LMC. Is it that we'll be able to figure out how the dark matter is changing as the galaxy evolves, or is that it, or are there some other questions that you're going to be able to answer as well?
Yeah, so I didn't explicitly say this in the abstract, but or I did in the abstract, but I didn't say it verbally. But previous studies have separately established that we need to account for the LMC, and other studies have accounted for the fact we need to account for the disk, but no studies have put them together. So we don't really have overall a current understanding of how the Milky Way galaxy evolved over time with dark matter. So that's one question that we're searching for. So over time, how did the galaxy form with dark matter? Like, what contribution did dark matter have in the formation of the Milky Way galaxy? And another one is we want just an overall understanding of how dark matter is distributed today in the present day Milky Way galaxy. How is it distributed? How much is there? So I think those are the two central questions that this project is trying to get at.
Awesome. I think that's going to be really exciting.
Yeah, it definitely is. No one's really done this before, so that's what makes it really exciting. It's very cutting edge.
Awesome. Do any of our other judges have any questions for Kiana? Anything? There's also a question in the Q&A, and the participants are welcome to answer them as well by typing them out, or we can save some for after everyone has presented as well. But if the other judges don't have any other questions, then we thank you, Kiana. That was a great presentation, and we will move on to the next one. So Kiana, if you could stop sharing your screen, and then I'll reshare and introduce our next participant. So next we have, okay. So our next presenter is Kayla Smith. So Kayla is analyzing the atmospheric chemistry of Mars, utilizing the Caltech/JPL 1D photochemical /transport model kinetics. This project, which has a manuscript and prepped, is very close to publication, is impact of noble water, the absorption cross sections on the present day Martian atmosphere via Caltech's JPL's 1D photochemical model. Kayla also works on another interesting research project to decipher Mars SMIF signals, and has modified the source code of kinetics to add and validate new isotopes. All 4 stable sulfur isotopes will be added to the model to decipher the impacts that the fractionation has on the atmosphere, and hundreds of isotope reactions to their model. Currently, Kayla is co-authoring a paper with Dr. Wong, Emilia Hernandez, UC Davis, and Vahab Raji, Georgia Tech, and Marissa Duckett, Emory, on what makes the planet Earth-like. So working on this manuscript with these amazing group of people has only enhanced her ability to ask more focused and precise astrobiological questions, but also exposes the beauty that lives within all life and contributing to the planet's, primarily exoplanet's, existence. So with that, Kayla, take it away. If you want to add anything, introduce yourself, and I'm looking forward to your presentation.
Awesome. Thank you so much. Are you able to see my screen?
Yes.
Okay, awesome. I didn't know. I can't hear. I can't see anyone. Okay, awesome. Well, hello. My name is Kayla. I am a rising senior at Central State University. And typically I am a Martian. I love Mars as my first love. And I have been doing research with Caltech for about 3 years now. But I came across this paper at AGU. My mentor, Dr. Mike Wong of Carnegie Science, he gave this talk on the process we call Earth, relationships between dynamic feedbacks, and the search for Gaia signatures in a new paradigm of Earth-likeness. We're basically trying to characterize how we can see exoplanets and how we can view them in an Earth-like way from a societal standpoint and a scientific standpoint. So this paper is currently in prep and I'm super excited about it. So let's go ahead and get started. Alrighty, so figure 1, that's a picture of our Earth. That is the only home that we have ever known. That is the only life that we have ever known to exist. In other words, this is life as we know it. However, when we start to look at exoplanets or we want to explore planets beyond our solar system, we have to open our eyes to understand that we may come across life as we don't know it, or anomalies of life. And so not only am I a big planetary science geek, but I'm super interested in astrobiology and learning about life in our universe. So when we find all these exoplanets, what are we going to do with them? So moving on to my little cloud here, number 1, what is Earth-likeness? So when I first got introduced to the paper, this is the first question I typed into Mr. Google, and Google told me that Earth-likeness can be defined as a scale from 0 to 1, where you can characterize all of these 5,000 plus exoplanets into a really small scale of 0 to 1. Now, that makes sense in hindsight, but is 0 to 1 big enough? Is 0 to 1 going to encapsulate the life that we may come across in this ever-expansive universe? And so we didn't think so. We didn't think 0 to 1 was big enough at all. So we loosely define Earth-likeness as a continuum of emergent entangled planetary phenomena. We take after Dr. Kara Cleland. She is at CU Boulder, and she says that if we put strict definitions on how we view life or how we try to define life, that may restrict us from understanding or accepting these anomalies of life that we may come across. So that is why we present tentative criteria for what life could be and what life is in the universe. Alrighty, so figure 2 takes us to a plot that basically wants to show the entanglement and intertwinement of geological and biological biosignatures. So we have Earth at the top. I can literally go outside right now. I can test the air. I can test the grass. I can test the soil. I can test the water. I can do hundreds of experiments literally right outside my dorm room now. I'm at Caltech. However, we cannot do that with exoplanets. We only really have the luxury of doing a flyby of these planets. And so how do we detect these exogeological and exobiological biosignatures? Well, if we want to loosely define another source of biosignatures, which we call Gaia signatures, we can look at the complexity of the planet's biosphere. So looking how the hydrosphere, lithosphere, and atmosphere all interact with each other and all intertwine with each other through time. So the higher and more complex the planet is, the higher the degree of Earth-likeness that planet actually has. And so this planet is tilted horizontal because it wants to represent a time scale going from left to right. And understanding that we don't have the resources to look at these exoplanets in great detail can open our eyes to a holistic approach to understanding these exoplanets. Alrighty, so equation 1 is a modified Drake equation. I don't know how many of you are familiar with the Drake equation, but it was proposed by Frank Drake in 1965. And he wrote this beautiful long equation that basically wanted to find the number of technologically advanced civilizations in the Milky Way galaxy. That seems very easy, right? I mean, that seems very approachable. Not really. So SETI is still actively trying to find these civilizations outside of our home planet Earth. And they're still trying to find if we can get a signal from any of these other potentially habitable worlds beyond our solar system. It's very difficult, but the equation itself is so beautiful in the sense that it actually acts as a framework. It's very flexible and malleable to where we can take things out, replace things, keep things in order to define what we're trying to find in our current paper, which is trying to characterize a planet of higher degree of Earth-likeness as other than Earth itself. And so here, I'm right here, N bio is a number of planetary biospheres. Epsilon P is a degree of Earth-likeness of planet P. Fi is the probability that life successfully integrated, Fi is probability of the emergence of life. Fg is the probability that life successfully integrates itself into Gaian-like or self-promoting planetary feedbacks. And then genicity is a new term defined by Wong et al. 2022. It's basically a new phenomenon to explain the planetary anomalies of habitability, or LIFE, which is LYFE, not LIFE. Great paper. You guys should all go read it. And it basically wants to characterize, if we're looking for life beyond our solar system, we have to be open to anomalies. So if N bio is a certain number, I feel like epsilon p, the degree of Earth likeness, can go up or down relational to how high the N bio number actually is, which relates to the complexity of the biosphere of the planet. So that's how that framework would work. And that's why I love the Drake equation. It really breaks down a very complicated concept into terms that I can actually understand. And I feel like if we can get to the point where we can actually detect or measure some of these variables, that would be amazing. Alrighty, so figure 3 is a plot that basically breaks down 4 of the main processes that happen on everyday Earth. We have the water cycle, plate tectonics, magnetic dynamo, and the carbonate silicate weathering cycle. So all of these are cycles that happen on Earth every day, every second, every minute, and they've been happening for a majority of Earth's life. However, these processes are dynamically persistent in the sense that they are persistent through time. The process itself has lasted generations and has evolved through an ever-changing Earth. But the process itself is dynamic in the sense that parts of it are changing. Obviously, the amount of water on Earth is drastically changing. The amount of volcanic activity is drastically changing over the course of its lifetime. And another thing I must point out about this plot is that the water cycle and plate tectonics actually feed into each other. I'll zoom in a little bit. They actually feed into each other. So they are also mutually giving each other positive feedbacks. So if I feed something into plate tectonics, it will feed back into me. And all of these things are essential to life on Earth. So if we could apply this framework to another planet that we could potentially find outside of our solar system, that means that that planet is very, very complex. It has a very complex and intelligent way of surviving and thriving. And so this so much isn't a really exact replica of what we would find on another planet, but it actually is a framework or a potential of what we could find on another planet that has habitable conditions. Alrighty, so figure 4 here is split up into 3 panels. So panel A is life and environment communicating with each other in a favorable way. I like to think of this as a Tesla, right? A Tesla is a self-autonomous vehicle, but something has to kind of push it to become autonomous. So let's say I'm life and the environment is Tesla. I could press a button on the Tesla and I could tell it to drive while I take a nap, which I don't recommend, but yes, people do it. And that Tesla would drive itself and it would be fine. It would be great. And this is the planet that we live on today. Life and environment are communicating in a self-promoting or Gaian feedback way or a self-autonomous way. So we don't have to tell the air to produce oxygen. We don't have to tell the trees to give off these chemicals that we need to breathe because it naturally does that. On the flip side of that, we have panel B, when life and environment do not communicate well with each other. I kind of put Venus or Jupiter or literally any other planet in our universe, in our Milky Way galaxy that isn't Earth, I would probably put that into this category in the sense that there may be some properties that may work, but a lot of the planetary atmosphere or planetary body is actually self-destructive, or we call these Median feedbacks. So where life and environment are not communicating with each other in a favorable way. And then panel C is basically when life and environment are communicating well in a sense, but then the environment just collapses. And then life from there, therefore, can express new genes or can communicate in a way that can re-encode itself to fit into the atmospheres or conditions of different environments. So I say pre-GOE and post-GOE, so great oxygenation event. If I'm a microbe living with no oxygen before the great oxygenation event, I'm loving it. Me and my friends are having a party. It's great. And then all of a sudden, the oxygen levels start to rise. I can either die off or I can re-encode myself to fit into this newfound environment that has a flux of oxygen. That is what this panel is saying. And that's honestly what happened to Earth. Some of the microbes and biological processes that existed pre-great oxygenation event actually exist now and have survived generations. And so we go throughout that in very great detail in our paper. Alrighty, switching gears a little bit, in part 2, my little cloud here, it's the cultural lens of Earth-likeness. So a section of our paper actually breaks down how Indigenous research frameworks and Indigenous scholars actually view the world as a part of us, their very intimate relationships with the natural world. And so Part one is we understand that Western science perspectives do not exist alone and do not intentionally bridge the inner workings of the natural world, also known as holistic approaches, which again, what we have to do for Earth-like exoplanets, because we can't look at them in piece by piece. We have to look at them in a holistic value, and Indigenous scholars really make a point to do this. Part two is seeing the intersections of planetary phenomena or coupled phenomena is a part of having a relational perspective. Destabilizing the world can disrupt homeostatic cycles. Again, Indigenous scholars really take into account how relational and how their spirituality, how they approach their science is really emerging from a life perspective to a environment perspective. So if I were to take away the water cycle, that would greatly disrupt the homeostasis of our planet. That would greatly disrupt the equilibrium that we are currently in. And part three is we recognize that the blending of cultures is what contributes to the sacredness of an Earth-like planet. An Earth-like planet would not be what it is without the big melting pot of people, ideas, ethnic backgrounds, races, everything. We are all essential to what makes our planet Earth-like. Okay, so quick significant takeaways. In this work, we do not define Earth-likeness with a strict, rigid definition. We characterize Earth-likeness with tentative criteria. 2, finding life on exoplanets is increasingly difficult, but utilizing the potential geological and biological Gaia signatures or biospheres or braids can create new parameters for biosignatures beyond Earth. And part 3, the natural world is meant to be embraced, studied, and valued. Thank you so much.
That was wonderful, Kayla. I really learned a lot. I've studied some biosignature stuff, and I've never heard of Gaia signatures. I thought that was really cool. So, judges, if you have any questions, I see Kirsten, you have your hand up. So, please ask away. Kirsten, you're muted.
Thanks. Hi, Kayla. That's super interesting project, super interesting work. Like I said, like Capri said, I also haven't ever heard of Gaia signatures. I was wondering if you could talk a bit more about, you know, I know that you talked about the Drake equation, but specifically a little bit more in depth of what a Gaia signature would look like in terms of observing a planet and you know, what would be the key components when observing a planet that we would need to be able to say, okay, this is X on our Gaia signature scale?
Exactly. Yeah. Thank you for that question. Thank you so much for the compliments. So if we are looking at a planet that is far away from Earth, that we can come up with all these criteria. It's in the habitable zone. It's not too near its co-star. It's not too far away from its host star. It's able to maintain liquid surface water. All of those things that originally popped off the top of our head, those are things that are really important. However, if we could see that a planet is able to go through seasonal changes, it's able to go through active weather, it's able to go through all these different intricacies within its planet where multiple different parts of the planet are communicating with each other in the sense that when it rains, obviously the ground goes through changes. And obviously when, you know, the water cycle, the water evaporates, the atmosphere goes through changes, and it all goes through this big cycle. If we can see that a planet is able to stably contribute to those cycles and it's able to maintain those cycles over a period of time, that's when we can say, okay, that's the degree of Earth-likeness or the amount of Gaia signatures that we're able to detect from this planet is quite high. So I would say that when the planet is able to internally communicate with each other, that's when I kind of describe it as, when the planet is able to intimately communicate with itself, but other planets in its solar system. I think that's when you can kind of start to take away those conclusions.
Yeah, that's super interesting. So in terms of, I have a follow-up question.
Yeah, no problem.
I don't know if you've thought about this. This might be putting you on the spot a little bit, but do you kind of have an idea of you know what sort of surveys that we would need to actually be able to detect these, you know, seasonal changes or interactions between, you know, the planet like you're talking about?
Right. So James Webb obviously is a huge contributor to that. In an ideal world, if Kayla had all the money in the world and I could just do whatever I wanted to do, I would probably have a probe for like each planet that we come across that has something from the outside that we can kind of see, I would just send a probe there and be like, yeah, let's probe it. Let's see what's in it. So ideally, I think a probe would probably be the best way to do that. Obviously, all these planets may not have a surface or whatever the case may be, or having an orbiter going around these planets to kind of detect the seasonal changes. If it actually has seasons, if it snows, what the clouds are made of, if there are any clouds, all those things come into account. And so in an ideal world, in a perfect world where Kayla just has a limitless amount of money, I would say I would probably put an orbiter and a probe around ideal planets. And then I think we get a better understanding of how these planets actually contribute to the Earth likeness that we currently kind of can conceptualize.
Awesome. Thanks.
Thank you.
Hi, Kayla. Great
Hi.
presentation. I just had a quick question. I'm not sure how much you or others have maybe thought about this, but when you're thinking about kind of like Earth likeness and these Gaia signatures, you're assuming that like the life that the planets or the bodies are going to be interacting with is going to be very like human-like or Earth-like.
Exactly.
And so when you're talking about the feedbacks that you might get, have you or anybody you're working with thought about what those interactions might be like if life is maybe not exactly as we know it?
Right, exactly. That's a really great question. So I don't know. I'm still learning a lot about the word complexity. The word complexity in the world of astrobiology is just a whole different subsection within itself. But complexity really boils down to the feedbacks that a planet is giving you, and then how those feedbacks can be characterized or how they can be conceptualized or compartmentalized. That's the best way I like to do it. So if we get like let's just say in a perfect world again, we send a signal out and a signal comes back to us. And it's very, very, very complex in the sense that we may not understand the language. We may not understand what the message is saying, but it's saying something. I feel like that's where the humanities honestly come in. Linguists, people that really break down what language is, people that break down how to decipher language. And then all those things kind of come into play. And so I think that if we were to find a planet that houses life as we don't know it, honestly, that could be whatever you want it to be. I mean, that could be literally the sky's the limit because we don't know. And so when you say life as we don't know it, it's kind of just like however you want to think about it. And that's very philosophical and very not straightforward. But I feel like it would just be a signal that we probably could not understand or could not decipher in our own human brains. But I don't think that makes it the feedback or the communication any less intelligent. I think that intelligence is not defined by if we can understand it or not, because we could be not intelligent enough compared to what we may find out there. You know what I mean? So yeah, I think that's a very deep question. I feel like that's a very, very broad question in the sense that we just don't know what life is. We don't know what it may look like.
Awesome. Thank you.
Yeah, Kiana.
Hey, great presentation, by the way.
Thank you. You
I
too.
am not an expert in exoplanets or any of these things, but it was really cool. I wanted to circle back to Kirsten's question about how you would go about sort of finding these things and finding these ideal worlds, because you said a lot that like in an ideal world, like limitless potential, money, this is what I would do. I would send out a probe. So I wanted to ask, what would be a more practical approach or a more practical solution?
Right. I honestly think we're already there. I think James Webb is doing a fantastic job in the sense that we are finding planets. I know everyone that studies exoplanets on here is like freaking out. Yes, I am too. I'm literally on NASA's website every single second. But yeah, I think James Webb is doing a great job in the sense that we're making these telescopes that are able to go farther. They're able to go into different parts of space in our universe. And so I think what we're doing right now is about as good as we could do personally. That's my personal opinion, in the sense that we are finding these planets. We are able to find out planets. We're able to kind of map solar systems, which is really cool. We're able to map the host stars and see these stars that are outside of our solar system. Like, I feel like we're doing pretty much everything that we could do currently. But yeah, I think that if we just continue to refine our technique, continue to refine our technology, and maybe we could send, I don't know, like a big spaceship that can have like 10 different telescopes popping out of it. I don't even know. There's the sky's the limit. And so right now, I really do think that we are doing what we could do in the sense that we are finding these planets, we are finding whole solar systems, we are finding these other like worlds that we're able to see. And we may not be able to study them in great details we may like, but that just kind of comes with the game. I think that's honestly the beauty of exoplanet work, is that, I mean, your questions may not get answered in your lifetime, but I know they will be answered soon. And I think that's just the beauty of studying the universe. I mean, the questions never stop flowing.
Oh, yeah, we'll take one last question right now from Gianni, and then we'll go to Justine's presentation. So Gianni, please ask your question.
Great presentation, Kayla.
Thank you.
I wanted to ask, I guess, where, or when you're trying to detect these or look for these exoplanets, like where are you primarily looking at?
Yeah, so so it's kind of weird. So my mentor, Mike Wong, he studies exoplanets. I think he studies, in our group, I think a lot of people study a lot of the WASP planets. I don't directly study them. I primarily study Mars, but on the paper, it's more of a theoretical, trying to get you to think paper. And so hopefully going into grad school, I will study exoplanets. I'm really starting to love those. But I think a lot of people are just trying to get as much information from the older solar systems that we have been able to study in more detail than the newer ones that we're finding. So yeah, I don't study them directly quite yet, but learning about them and learning about if we were to find these planets, what would we do? I think are the biggest questions, that we're finding them and they're there, but what are we going to do with that information? And so I'll get back to you on that. When I start studying exoplanets in great detail, we can have a chat.
Awesome. Thank you so much, Kayla, for
Thank you.
Your presentation. That was awesome. So I will go ahead and introduce our next presenter. So our next presenter is Justine Singleton. So Justine is an undergraduate rising senior majoring in astronomy at Cornell University. She has been researching pulsars since her freshman year. Her current research is related to the work of the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, which seeks to detect gravitational waves through pulsar timing. She's generally interested in compact objects. So compact objects, this project involves using PINT to analyze the fit of timing models for Black Widow pulsars. Another project she'll be working on this summer is related to the timing of millisecond pulsars in globular clusters. So I will stop sharing my screen, and Justine, please take it away.
All right. Okay, can you see my screen?
Yes.
Okay. I'm Justine, and I'm going to be talking about Black Widow. Am I still sharing? I got a message that said Zoom quit unexpectedly.
We can still, me personally, I can still see your screen and your poster, and I see some other thumbs up. So I think you're good to go.
Okay, I think I'm back. Let me try sharing again. Okay, can you see it again now?
We can.
Okay. I will be talking about Black Widow pulsars. So pulsars are a kind of neutron star that emits beams of radiation as it spins. And millisecond pulsars are pulsars that spin on the order of milliseconds, and they're most commonly found in binary systems. So Black Widow pulsars are a kind of binary millisecond pulsar where the companion star has a mass a lot smaller than the pulsar, around 0.1 solar masses. And the pulsar is accreting material off of the other star, which is why it's called Black Widow. And having a better understanding of Black Widow pulsars could help to improve pulsar timing arrays. Groups like NanoGrav are working on timing pulsars and the idea like how often they spin and what the spin rate And because when the pulsars are consistent, that they can be accurate to the same level as atomic clocks. But sometimes they aren't consistent, and sometimes we have trouble telling like what period it has. And so for Black Widow pulsars, there can be variations in the orbital parameters, so it can be a bit more difficult to use them. And this study looks at the pulsars J1705 1903 and J610 2100. These two graphs on the left are the residual plots for both. I can try to zoom in.
I think Justine might be having some technical, is Justine frozen for anyone else, or is it just, okay, I think Justine might be having some technical difficulties. So while we wait, I want to give her time to shine. So while we wait for her to come back and for everything to unfreeze, did anyone have any other questions for anyone that's presented, or if Justine is back, then we can proceed with her. I think her Zoom might have gone off, but yeah, while we're waiting for Justine to for the technical difficulties, anybody have any questions for any of our other presenters or anything while we're waiting for that?
It looks like there's a question in the chat, or not in the chat. Well, also it looks like a question in the chat, but also one in the Q&A. Someone asked, and I believe this is for Kiana, what do you mean by the disk depletes the subhalos?
Okay, that's actually a great question. And I have visuals for this. I couldn't fit them into my poster. Is it okay if I share visuals from another presentation?
Yeah, I'll keep a lookout for Justine to come back, but yes, really quickly, just so we can.
Very, very quickly. So this is a great question. So basically this has to do with an effect called tidal stripping. So this basically happens when you have, so because the center of the Milky Way, the disk, carries so much mass for the galaxy, any smaller sort of satellite galaxies or subhalos that get close enough to that disk, the gravitational effects will be so strong that it'll actually rip away stellar material from the smaller subhalo or galaxy. And so that's an effect called tidal stripping. And the result of that is called depletion. So the smaller satellite galaxy or subhalo is being depleted by that mass, that disk at the center of the galaxy. I hope that answers the question.
And then it looks like there was a question from Rob in the chat. And I think that this might be for Kayla. Would you rather focus on redefining computational methods or instrumentation?
Yeah, I was just messaging him back, but yeah, I'll answer it out loud. So thank you so much for the question, Rob. I truthfully think that computational methods need to be defined or redefined more. I think that we have a lot of good instrumentation right now. I think we should take what we have now and kind of see where we get with this. But I truly think that finding these planets, which we are finding them, but I think characterizing them is the hard part. I really, really, really do. I mean, we have the highest resolution that we could possibly get to, the best technology that we have right now. like, I don't really know what else we could do instrumentally wise. So I really think computational can use some help. I think that actually characterizing them and actually sorting them into a way that we're seeing them just needs to be fixed a little bit more. It's really, really hard because we're not next to these planets. Like, we're literally hundreds of billions of light years away. It's very difficult. But I really, really think that computational methods could use some tweaking, but I think we're also just doing really great on the instrumental side. So that could be a little bit of bias there.
Cool. And I actually have, so hi, this is Capri. So I actually, while we're still waiting, hopefully for Justine to join us back here, I have a question for Kayla. I've actually done some work on detecting potential biosignatures with like JWST and some just work on biosignatures in general. And so I was wondering about these signatures, if like there are plans to kind of look at some maybe false positives or things that can be caused by naturally occurring like geological processes to distinguish these two, that from actual signatures that could be caused by life producing organisms or anything.
Right. And that's really, really difficult. That's really, really difficult to differentiate because, I mean, it really just breaks down what you define life to be, because people may take a geologic standpoint and how life could thrive, and they may take a biological or metabolical standpoint. It just really depends on what you are looking at life as. And that's a whole philosophical thing that I'm still trying to unravel because it's very intricate. But once you do that and you find you're comfortable with how you define life, I think at that point, looking at a holistic value of the planet is really, really important, but also looking at how things are interacting with each other. I really think that if we could see how the geological structures are interacting with the atmosphere, if we could see those in real time and see those things in really, really intricate space, I think that would determine if life is causing it or if it's just the planet as a whole doing its thing. And so I think just creating those boundaries in between what you're looking at. So if I want to look at atmospheric processes, which is what I do on which is what I do on Mars, I would try to I do take some geological implications and ramifications, but I may look at the atmosphere. So I may see how the geologic features impact the atmosphere. So one of my projects is actually looking at water isotope or water absorption cross sections escape. So how did water leave Mars? And so we think a lot of it escaped to space, which means that a lot of it had to be sucked up into the exobase of the atmosphere. And so that means a lot of it had to be stripped away from solar wind, from the sun. And so all those things come into contact. Seeing how it literally went from the ground to the atmosphere to the space, seeing how all those are communicating with each other is very, very important. So that's a very long-winded way of saying just how is the planet communicating with the different aspects of the planet, how are they communicating with each other?
Awesome. Thank you for that great answer. I actually have another question for Kiana if no one else has any other questions. The judges or so please excuse like my total maybe ignorance about this, but is like I think it was like what you were studying, does this only apply to like a certain type of galaxy, like spiral galaxies or anything? Are there other types like elliptical or anything?
That's a great question. So the study of dark matter is often intertwined with the study of galaxy formation and evolution, because so many galaxies in the Milky Way are like the Milky Way. And even further, there's so many satellite galaxies, dwarf galaxies, that are just populated throughout the universe. So if we get a good reading, a good constraint on the dark matter in the Milky Way, and the dark matter in these dwarf galaxies, we can extrapolate further to other dwarf galaxies throughout the universe and other galaxies like the Milky Way. And we're really increasing our understanding of dark matter from very little to at least we have something, some understanding of dark matter in some significant portion of the universe, even if it's not the entire universe.
Oh, thank you so much. So Justine, we were just asking questions while you were sorting out some technical difficulties. Are you able to share your screen, or would you like me to share it for you and you present that way? What would be the best way for you?
I can try sharing again. Hopefully it will not freeze this time.
Okay, just let me know. We have the slides as backup, but I will let you go ahead and share your screen.
Okay. All right. So Black Widow pulsars are a type of binary millisecond pulsar where the mass of the companion star is a lot smaller than the pulsar. And the pulsar is accreting material off of the other star. So that's why it's called Black Widow. Understanding Black Widow pulsars could allow for advances in pulsar timing arrays. So groups like Nanograv time pulsars in order to detect gravitational waves, because pulsars, when they're timed properly, can be as accurate as atomic clocks. And so if there's a shift in all of these pulsars, then there's a good chance that there are gravitational waves that have passed through. But some pulsars aren't easy to time, and Black Widow pulsars are difficult to time because of the variability in the orbital parameters, because sometimes there's material that sort of clouds around the binary system because there's matter being accreted off of the other star, and sometimes there's radio eclipses from the companion star passing in front of the pulsar. So all of that can cause a lot of noise. And this study is about the pulsars J1705-1903 and J610-2100. And these are the residual plots for their orbital phases. And you can notice that around 0.25 for J1705-1903, there's a lot more noise than in the rest of its orbital phase. And that's because it's at conjunction, and there's a radio eclipse happening during that point in its orbit. And both of these pulsars are part of the Nanograv data set. And so this project mainly focused on improving the fit of the timing models for both of them. And so I was excising the times of arrival, or TOAs, around conjunction for both of these pulsars at different ranges. Like for the graphs on the left side, it's from 0.15 to 0.35 in phase, and then for these graphs on the right, it's 0.20 to 0.30 in phase. And so the point was to see what range of removal best improved the fit for both of these pulsars. And this was analyzed so far through mean and standard deviation and reduced chi-squared of the remaining residuals for both. And this is still in progress, but what I can say is that the best range of removal so far has been different for both pulsars because of their different sources of noise. For instance, J1705-1903 has radio eclipses, but J610-2100 does not. It has noise from other sources. So they need different methods of improving the timing models. And in the future, this could be extended to other Black Widow pulsars and to include the effects of other things like dispersion measure. That's it. Thank you.
Nicely done. Even with technical difficulties, you did amazing. So our judges, do you have questions for Justine? If so, please just unmute yourself or raise your hand.
Hi, Justine. I have a question. So I'm going to preface this with I don't do anything with pulsars. So this might be a very obvious thing, but I know that you were saying that by studying these Black Widow pulsars, you would be able to advance the pulsar timing arrays. So what does it mean to advance pulsar timing arrays, and how is that beneficial, for science moving forward?
So for pulsar timing arrays, you want to have as many pulsars as possible so that if there's a signal, you can double check that it isn't just something in a local area, that it is actually gravitational waves. And then you want to have the signals for all of the pulsars that you are timing so that you can make sure that they're consistent, because sometimes pulsars can be irregular due to properties in the neutron stars themselves. And then sometimes there could be other signals that are being picked up instead. So to advance the pulsar timing array, I'd say it's to make sure that the signals are as clean as possible, like reducing the amount of noise and then having a lot of pulsars so that you can pick up more.
Awesome, thanks.
Augustine, I wanted to say a great talk. I just wanted to ask real quick. I think you might have already explained it, but I just wanted to know like more of your future works based on the results you had in your project thus far.
So in the future, I could extend this to other Black Widow pulsars because this so far has only been using 2. And then I could also include other effects because this is mainly focused on just removing noise around conjunction, which might not be the best thing for pulsars that don't necessarily have radio eclipses.
Awesome. So it looks like we have Justine, great presentation. We have a question from Don Dixon in the audience about how does accretion in Black Widow, Widow, I think Widow, sorry, pulsars affect the rotation of the pulsar? Does the accretion spin up the pulsar or just regulate the constant spin is what Don is inquiring about.
I'm not sure how it would affect the spin of the pulsar itself, but it could affect the binary orbit because the companion star is getting lighter. I haven't been studying the dynamics of the system as much, so I can't really give a concrete answer on that, but it would definitely affect the orbit.
Awesome. That was a great response. Let me see if there are any other questions from anyone in the judges or fellow participants for Justine. All right, so Justine, you can stop sharing your screen. Great presentation. You handled that like a pro. So yeah, so this is, unless we don't have any other questions from the audience, this was our undergraduate research showcase. We're really glad that you all joined us for this. So I hope you all have been enjoying your week. I just want to say congratulations to all our presenters. Y'all did amazing, really great posters. And thank you to our judges. So tomorrow is the last day of Black Space Week, and we have a cultural astronomy panel at 8 o'clock Eastern Time. And then we also have a mental health and group meditation session at 12 p.m. So we hope that you all will join us for that and that you've been enjoying Black Space Week